everyone. My name is Kennedy Corey. I'm currently a senior biology major here at Tougaloo College. And today I'll be telling you all about a little research I did this summer. So the theme of my research, or the title, was measuring impurities in commercial eggshell membrane capsules using dual excitation Raman spectroscopy. And this research was done at Jackson State University in the Department of Chemistry, Physics, and Atmospheric Science under Dr. Shan Yang, and it was funded by Mississippi Embry. So just a little background about my research, why it is important. So when we talk about eggshell membranes, which of course is the membrane that you can find just in like a regular egg, that you can buy from the grocery store. So research in the past has proven that these eggshell membranes are supposed to help with joint support. So when we talk about osteoarthritis and people who have aging joints, some research proved that if they took, eggshell membranes, or they ate them or took like commercial capsules, that it was beneficial. The eggshell membranes help with pain and like reduce inflammation and whatnot. So we know, of course, that when you have commercial capsules, there might sometimes be things that are mixed in them. They might not just be like pure eggshell membrane. There has to be something there that makes sure it can be grinded down into a capsule. And also, we also knew that it is very hard to get the membrane off of the shell. So there was also a possibility that the shell might still be in the capsule as well, because extraction from the egg is not easy. So we decided to test this and see how much shell to membrane was present in the capsule. So in order to do this, we created three different concentrations. So we did 1:1, 1:2, and 1:5. And this is basically membrane. And we can see this in the methods right here. So the 1 on the left side of the ratio represents the membrane. And it is equal to 0.01 grams of membrane. And the right side corresponds to the eggshell. So when we say 1, that is always just the pure membrane. And when we say on the other side 1:5, that is also always going to be the eggshell. So in a 1:2 ratio, there's double the amount of shell as there is of actual membrane. So just some results. And this one right here, this is basically what we use to measure the spectrum, and the difference is we used Raman spectroscopy. So if you see right here, this blue line is the natural eggshell, which means that the natural eggshell has a peak right around 1100 and has a peak right around 700. And then we see the natural eggshell membrane is the red, and those peaks are around about 1450 and then about 1650. And then what you want to look at in comparison is the commercial powder. So we can already see before we even did our concentrations that the commercial powder, yes, it has the peaks at the eggshell membrane, which will be right here, but it also had a little bit of a peak at the eggshell, which we already knew then that there was shell present in the capsule. But further, we wanted to know how much. So we come down here, and it's important to look at the commercial powder is the red line. And you can see it is between the green and the black. So the green is the ratio 1:5, and the black is the ratio 1:2. So just by these two graphs, we've already figured out that the commercial powder more than likely has double the amount of eggshell in the capsule compared to membrane. And if you're giving people commercial eggshell membrane capsules to help with joint support, but you have all of the proteins of the shell, double the proteins of the shell and not as much of the membrane, how like accurate, how good of a job are your capsules doing with joint support when the proteins that we need are the proteins in the eggshell membrane and not in the actual eggshell? So also, we come over here to the figure 3, try to zoom in for you. So we actually measured the peaks. So the average of the difference in peak heights of the eggshells and the egg membranes of commercial powder and ratios are plotted on the x-axis, and the average, which is located on the y-axis, was calculated by measuring the difference of the shell intensity of 10 data points by the difference of eggshell membrane intensity by 10 data points. So this is basically just giving the average of like the height on the Raman spectroscopy. By the way, Raman spectroscopy is basically a laser that measures absorbance. So right here in the 1-to-1, there was average was 1.23. Yes, 1.23. The commercial powder was at a 5.85, and then the 1-to-2 was at a 13.87. So we can very easily say there's more shell in the capsule than there is actual membrane. So in conclusion, if I can get this portion. So the commercial powder did have a higher intensity for the natural eggshell peak than the natural eggshell membrane peak. And the commercial powder had about 3 times as much eggshell as membrane. When we're comparing the ratios 1-to-1, 1-to-2, 1-to-5, the commercial powder lied between the ratios of 1-to-1 and 1-to-2. And based on 10 different measurements of the commercial powder. So that means we shook it up and we lasered it with the Raman spectroscopy 10 times. The average of the difference in the eggshell peak to the egg membrane peak is a 5.85. So this data was very helpful, but of course, in any experiment, we did have a few issues. So when it comes to future directions, even though we actually use liquid nitrogen to mesh up our natural eggshell membrane in order to get it to like a powdery base so that it can be measured under the Raman spectroscopy, because the laser is very specific. So if you have like a really thick piece of membrane, it's only going to scan that like one area. So you have to make sure it is the powder in order to get like several flakes. So even though the liquid nitrogen allowed us to make the egg membranes much smaller than the oven did, because we used the oven at first, did not work to make it powdery. It did not fully produce all of the membranes to become a full powder. We still had issues with the liquid nitrogen as well. So in the future, another technique could be used to make the egg membranes even smaller. And additionally, another way to make our experiment more accurate, if those membranes can't get much smaller than they currently are, we could also think about using a laser with a larger diameter. So basically, instead of one that is like really small, using like a thicker one so it can get like more of those materials so it could be more accurate. So thank you all so much for viewing my poster, and I'll see you later.